Next we have exercise 12.4.4 where we have to prove lemma 12.4.9. So let's start by recalling the statement of the lemma. So this is the statement of lemma 12.4.9 written briefly. So x comma d of course is a metric space in which we have this Cauchy sequence xn, and this sequence has a subsequence xnj which converges to some point x0 in x. Then the original Cauchy sequence also converges to that same point x0. This is what we have to prove. We start the solution by choosing a positive epsilon. Because the sequence xn is a Cauchy sequence, for this epsilon there will exist an integer capital N greater than or equal to small n, which is the starting value of the index n, such that the distance between these two terms x alpha and x beta is less than or equal to epsilon divided by 2 for all levels alpha and beta greater than or equal to n. This happens just because this is a Cauchy sequence. Now we are also given that our sequence xn has a subsequence xnj that converges to a point x0. So you see the statement of proposition 12.4.5. It tells us that then that x0 becomes a limit point of our original sequence xn. So for this epsilon and this n, there will exist an integer gamma greater than or equal to n, such that the term x gamma of our sequence satisfies this inequality. That means the distance between x gamma and that point x0, which is a limit point, is less than or equal to epsilon divided by 2. This comes from the fact that that subsequence xnj converges to x0. So for all integers small n greater than or equal to capital N, we consider the distance between the term xn and x0 by triangle inequality, that is less than or equal to the distance between xn and x gamma plus the distance between x gamma and x0. Now this is less than or equal to epsilon divided by 2 because of this. However, this happens only when the levels alpha and beta exceed n. I mean, they are at least n, at least capital N. Is that the case for n and gamma? Well, we have already chosen n like that. Small n is greater than or equal to capital N, and gamma is also greater than or equal to capital N here. So that is why this is less than or equal to epsilon divided by 2 from these inequalities, and this anyway is also less than or equal to epsilon divided by 2. So their sum becomes epsilon. So we have now found that for our chosen any positive epsilon, there exists an n such that if we choose the level small n at least as large as capital N, then the distance between the corresponding term of the sequence, that is xn and x0, is less than or equal to epsilon, and hence our sequence xn converges to x0. So that's what we wanted to prove. So the solution ends here. Next we have exercise 5 where xn is a sequence in a metric space x comma d and let L be a point in x. Now say our sequence has L as a limit point. Then we have to prove that L is then an adherent point of this set, which is the set of all terms of our sequence. And we have to also answer if the converse is true. That means if L is an adherent point of this set, then is it necessary that L will also be a limit point? And the first half of the solution is just this. By propositions 12.4.5 and 12.2.10, L is an adherent point of that set. I won't explain anymore how exactly this is the case. You go and see the propositions, it will be clear to you. So next we see the converse part. The converse is false. You consider the space of real numbers with the usual metric, and there you consider the sequence of all natural numbers, which you already know has no limit point. But in spite of that, each natural number is an adherent point of the set of the terms of this sequence, and this set is again just n, the set of natural numbers. So each natural number is an adherent point of this set, but none of them is a limit point of that sequence. Next, exercise 6, where we have to show that every Cauchy sequence has at most one limit point. That means if we are given a Cauchy sequence in a metric space, either it has no limit point or it has exactly one limit point. This solution is also pretty easy, so easy that it's just this line. Apply proposition 12 for 5, lemma 12 for 9 and proposition 12 120. It's up to you to figure out exactly how these things, when considered together, prove this fact. Let's see another one, number 7, where we have to prove proposition 12 for 12, that last one. And this is the statement of this proposition, one half of it actually. Let x comma d be a metric space and let y be a subset of x. If the subspace y is a complete metric space, then the subset y is closed in x, that is part A. And the solution to part A again is like that. Apply lemma 12 for 7 and propositions 12 120 and part B of proposition 12 215. Looking at these things, going through the statements of these things, you should be able to figure out why. And next we have part B of the proposition. Here the metric space, the original one, is itself complete and it's given that the subset y is closed in it. Then we have to prove that y as a subspace is also complete. And the solution to part B is just this. Apply proposition 12 to 15 part B. That's it. And let's end the video here itself. Next week we are going to solve the only other exercise that is still there in this section, number 8, which involves completion of a metric space. If you are given a metric space which is not complete, then it sits inside a larger metric space as a subspace, and that larger space is complete, which is called a completion of this space. So next week we will construct that.